Tasha Arvanitis and Dr. Dong are the only people left in the world who can explain modern physics. But Dr. Dong is busy writing the next death sentence of a quiz. So, Tasha is the only one left. She will explain it to us. Or will she? Tasha Arvanitis, here to explain it all. Quadis Evans, the learner. Haley Ramirez and Shari Duvall, here to save the day.
How do you find the probabilities associated with distinguishable dice?
Well, that's easy. A distinguishable die is basically like a distinguishable particle, with probabilities associated with each individual particle. So, for instance, if you have a proton...
Think we can do it, Shari?
I don't know. It's a pretty tough case, but I think we got it.
I think we can do it.
So, Quadis. We have these dice.
Let's start with distinguishable particle. Here you go, Quadis. Let's use these dice. Go ahead, roll them. The probability of rolling a 6 on this die is 1/6. And the probability of rolling it on this die is, again, 1/6. It's just like regular probabilities, because these two dice are distinguishable. See, you can tell them apart. This one's red, and this one's white.
Of course.
Right. So, say we wanted to find the probability that the dice would add up to be 5. Now, we can write out all the possibilities. Now, out of these, which ones would add up to be 5?
1-4, 2-3, 4-1, and 3-2.
Exactly. So, we have how many possibilities?
4 out of 36.
Exactly. Or, if we want to reduce our fractions.
1/9.
Exactly.
So does that make sense?
Yeah, that wasn't hard. How do you deal with probabilities in identical bosons?
Identical bosons are trickier than distinguishable particles because we can't tell the difference between them. So, like, if we have, let's say, 2 electrons, E minus, E minus, and they interact with a photon, and then they come out, we're not sure which one's which, because they could well have switched places in this mysterious box of an interaction, right? Extra electron there. And so the wave function is a little longer, because we can't... So, as you can see, it's a bit longer, it's a bit more complicated, and the probabilities are different. Fundamentally different. Get it?
We're here to save the day.
Again.
So let's move on to identical bosons. We'll use these dice now.
Those are identical, right? You can't tell the difference between them.
Yeah.
So, since they're identical, the probabilities aren't dependent on the order. So, for example, rolling a 5 and a 3 is the same as rolling a 3 here and a 5 here, right?
Yeah, I get that.
So if you get it, let's see if you can do it this time.
Cross off which ones wouldn't matter.
And remember, you only need to cross off one of each.
Good. Now, do you understand why that is?
Yeah, because there's a 2 and a 1 here, and there's a 2 and a 1 here.
So,
the order doesn't matter.
So what's your new denominator?
Identical fermions are like identical bosons in the fact that we don't know whether the one that went in is the one that came out. So it has, again, a very long wave function. However, instead of a plus sign here, it has a minus sign because of the difference in intrinsic angular momentum between bosons and fermions. Fermions, by the way, are the things that make up matter, while bosons carry energy. The minus sign here says that if psi1 equals psi2, then the particles don't exist. So the Pauli exclusion principle takes advantage of this and says that fermions can't have all the same quantum numbers at the same time.
We're here to save the day. Again.
So, Quadis, these dice are identical, right?
Yeah.
So we did identical bosons. Now let's go to identical fermions.
Now, identical fermions are very special. They can't have all the same quantum numbers, which means that you can't roll doubles. So, like, the probability of getting 2 6s is 0.
Right. So now let's go back to our chart. Which of these would not be a valid roll when we are using identical fermions? Very good. Now why is that?
Because they're all doubles. And with identical fermions, you can't have doubles.
Right. They can't be in the same state. So now let's say we wanted to, again, find the probability of rolling a 5, a sum of 5 in identical fermions. How would we do that? What would that be?
The sum of the probability of finding the sum of the fermions would be
Time for a connection to the quantum world.
Fermions are like particles in matter. They can't be in the same state at the same time because of the Pauli exclusion principle. Does that make sense?
yeah. What's the Pauli exclusion principle?
It states that an identical fermion cannot be in the same state at the same time. Two identical.
Cool.
Now do you understand?
I understand.
So, how do you feel about quantum statistics, Quadis?
Pretty good, Haley. It's actually not that hard. Once it's explained well.
I explained it in perfectly understandable terms.
Whatever.
Right.
So, Quadis, you know how to do it with 2 dice. Now, let's try to find the probability when we have 3 dice. If we wanted to roll a sum of 9, would we want to use distinguishable particles, identical fermions, or identical bosons?
I mean, I can write them all out.
Why bother? You can just write a program. It's pretty quick, not too hard. So you end up with 25 out of 216 with distinguishable particles, 6 over 56, so that's 3 over 28 identical bosons, and 3 over 20 for fermions. So that's 0.1157, 0.10714, and 0.15. So yeah, you better go with fermions.
Yeah, sure. All right.
Quadis, why don't you solve it?
The hard way.
So there are 216 possibilities, of which 25 add to become 9. So the probability that we will roll a 9 with 3 distinguishable dice are 25 of 216, which reduces to become 0.116. For identical bosons, after crossing out all the repeats, there are only 56 possible rolls left. Of those, 6 add to be 9. The probability is 0.1. For identical fermions, after crossing off all the doubles in addition to crossing out all the repeats, there are only 20 possibilities left. Only 3 add to be 9, leaving us with a probability of 0.15.